I supposed to give this talk, and I previously gave it with my colleague, another Sergei. Unfortunately, he was not able to come today. He was so excited about visiting New York, so he broke his leg, and he's not with us today. But I definitely tried to learn the other part of this presentation, so I probably will be talking about right things, hopefully. But my name is Sergei. I'm a technical lead for Kotlin infra team at Meta. For the past 3 years, I'm working on Kotlin adoption for probably the biggest mobile app code base that exists. Today, we are going to talk about the challenges that we faced over these 3 years, how we pivoted our code base from being million lines of Java code to a code base where millions Java, Kotlin, and other languages lines of code coexist. And yeah, does it actually sound like a good idea to talk in 2022 about the Kotlin adoption? Like, Kotlin is with us for many years now. But yeah, probably it's still a good idea to talk about this because we are facing different challenges through these years, and they actively change together with their language evolution. Before getting into scale and imagining what is the giant code base, let's first try to understand what are the typical project we write with Kotlin, how we adopt Kotlin there, and then we can adjust our findings to the code base at scale. Like, when you imagine a typical project, what is so special there? So maybe when I do imagine this thing it's at 10, probably 100 modules there, 100,000 of lines of code, and like tens of developers. JetBrains optimized a lot the Kotlin startup documentation and everything like this to fulfill the needs of this project, and they did it amazingly, and Google definitely helped with this. But what is the adoption in this project looks like? So we probably write code in Android Studio, and it's absolutely fine. We just added a few build script to make it work with Gradle, and finally we are shipping probably a slightly bigger application to a Play Store, but it's all fine. At this scale, we probably don't see any problems. What we care about is delivering the business value as soon as it's possible at a good velocity, and this is what developers care in typical project. Now let's try to get to a project at scale, a really big one. In the title, I mentioned the giant Java application. Probably we need slightly a better definition of scale or a big project. Hundreds of thousands of modules, tens of millions of lines of code, and finally thousands of developers. So this is a scale of Meta family of apps. Most of the content of this talk is applicable to the application when they reach at least probably 10% of this scale. However, some of the optimizations and techniques are applicable even if you have a smaller code base. So let's move to the adoption at scale. And you might wonder what is different. We still need to write code in Android Studio. Can we do this? We still need to build things somehow. Is it possible to do it with Gradle? And then we finally need to ship probably a slightly bigger application to a Play Store. Unfortunately, the answer for all of this question from the very beginning was no, we can't. It's not possible. Probably we should not adopt Kotlin at all. However, over the years it changed. The first blocker for us was the application side that was a hard blocker for any further adoption. Then we get to Android Studio because we were not able to write any code, and then the build speed hit it. But let's go through the all steps of adoption. First we write code, then we build it, and finally then we ship it. Let's try to dig deeper into all of these stages. To write code effectively, we need a few tools. Our favorite IDE, of course, a place where we have spent most of our productive time as the engineers. A long list of tools to maintain the quality of our projects, linters, formatters, anything like this. And finally, some libraries and SDKs to use Kotlin as a first citizen in the code base. And of course, all of these have some problems. Some of them are new to the project at scale. Some of them also exist in the smaller ones. Meta works in a huge monorepo. It's even complicated time to time to check it out, and like it's a facepalm sometimes. What should I say even about opening all the project in IDE? It's not obviously possible to process hundreds of thousands of modules in memory, so we either should load, unload modules whenever we need, or move to some kind of bigger machines and do something smart about this. Android Studio for Java can have around 1,000 of modules continuously open, and it's optimized to take care of these capacities. However, in Kotlin, the numbers were probably 10 times lower. So with just 100 of modules, it was not possible to do even small refactorings, and there's nothing need to say about the even bigger ones that required for the whole app, let's say Instagram, or like even the family of apps code base. Why? There are many factors. One of them is that just Kotlin is a more complicated language, and it will be an answer for many things during this presentation. Another thing is Kotlin compiler plugin and how we plug it into the IDE. It was not in a great state for a while. However, there were many improvements there over the years, but it's still, we had to jump in and fix a lot of things that were important for us. And just to give you some understanding, this is how our render looked like. And no, it's not my video here that is slow or my slides lagging. It's definitely the first experience of Kotlin at Meta, so we just opened something, and it was not possible to render even some functions and constant, so it was all the mess. It took us roughly 8 months to get to the state where it was possible to write code for the developers of our applications. We immediately added, before this, we immediately added restriction to lower the language spread in the code base and allowing Kotlin only for specific places that are not so close to the critical compilation path, so we can handle them. Okay, we have problems, we understand them. But how to detect the root causes? The easiest and probably the first approach that we need to apply is let's treat IDE as just an application, a Java application, a native application, whatever. But what should we do? We should get some samples from our users, how they use it, how the process behaves, what allocations we do there. Everything is important. Or do a heap dump if it's something VM-based, and just analyze this. But it's not the only option, and for us, the first attempt didn't work well. So it's also possible to add custom analysis and tracing to your IDE, but the only but is if you're ready to maintain a custom fork of your IDE. Fortunately, Kotlin plugin was open sourced, and we were able to get into it and edit the tracing for the major use cases that we have at the company. After that, we had a good digital footprint of what our users are doing, and we got another important metric is how much time developers spend running or editing Kotlin compared to Java. And in the next few years, it was our major customer metric that we tried to improve to make sure that adoption is going at a health rate. So we ended up maintaining a fork, but that's not too bad. Only a few engineers help us doing this. Let me now guide you through probably top 2 of the cases that we have, and I like them most. So my favorite one is the touch bar icons and how it frees most of our developers' machines. It's a funny one. Anyone in the audience like the touch bar on your laptops? No? Me neither. However, I still have one. Probably should get rid of it. In Android Studio, touch bar interactions, the custom icon that you might have in a touch bar, were not good at all, like from the design to how they interacted on the main thread. We had freezes on the new developers' machine. At that time, they just got the new shiny MacBooks. And how it happened, even if you didn't use the touch bar as customized icons, IDE rendered the whole touch bar for you, but then it just dropped it without actually rendering it inside the touch bar. So we just wasted time on the whole fleet of our user machines. Luckily, JetBrains helped us to fix this one, and years later, Apple decided to provide a hardware fix for this issue and finally remove the touch bars at all. Another issue, not a big secret that we're not using the Kotlin multi-platform in most of our apps just because we are okay with developing native things. And however, our Android developers experience some of the issues with multi-platform elements in IDE. So in a custom fork, we had to get rid of almost everything that is related to multi-platform at that time. Here, there is a tiny icon for expected and natural behavior in our gutter. Surprisingly, some of the really heavy computations was done to make it render in your IDE. So it was a synchronization block that didn't allow it. So again, we interacted with JetBrains here, and thanks to them, it was fixed. We completely removed the multi-platform actual declaration and anything like this, so it's no longer a problem anywhere. And just to get an understanding, so on the left it was the state of analysis before we implemented the fix here and delivered to user, and on the right is just what happened after. So it was a roughly 60% improvement in analysis time whenever you have an indexed expected actual behavior, which is now in almost every Kotlin SDK library. So quite a big improvement. So it's done on the right already. Okay. What else we do in addition to writing codes? We probably interact with people, but here what is more important for us is that we do a code review and interact there about some codes. We have a lot of tools to maintain and support our developers while they do inner cycles on their laptops and then doing their outer cycles in CI and further. All this helps us to maintain quite good standards of code and ship it then to users. Let's get into linters first. So we need to ensure that mistakes are really hard to make as hard as possible in our code base and support developers everywhere. In code style, code formatting, and safety, some probably even race conditions. If it's possible to detect something like this in the code base, it would be awesome. However, most of these tools were not available. The first we touched Kotlin. So some of them Google brought to the community in a while, like all Android links were done by Google or any other tools you might notice from the public tool chain. But our internal tools needed to be in a better shape to support Kotlin. And internal tools, what they need to understand to support your better Kotlin development. They need to understand the Kotlin AST. And to understand this Kotlin AST, you need to deliver this both to a browser and to the machines of your users and to Android Studio. So you need some sort of a tool that recognizes Kotlin grammar everywhere. So there are some of them. And we also implemented one. So, for example, here you can see a few checks that we did to understand that something is unsafely dereferenced, or even find out that the complexity of the method increased during the changes that engineers applied. So, for example, this complexity increase check is provided by an infer tool, which is a static analysis and open source. You can check it out. All right. Formatters. Code formatting is quite important, and for us, unfortunately, none of the public and open source tool helped, mainly because the code base is too large to handle any open source standards or cover all the cases that we need. So mainly our concern was the performance and the ability to get to 100 symbols in a line of code without significant changes in developer velocity in reviews. So the problem with KT-lint, which is quite a public standard these days, was the 100 characters per line width. So we had to come up with another solution, which was a KT-FMT, and which is based on the public open source Java formatter from Google. So KT-FMT is also open source if you're interested to check. But here are some of the difference. Mainly the focus was to place everything that we need, the long names or long function calls in a chains to be sort of readable and to be easy to make a difference in our review CI. So, and this is how IntelliJ formatter behaved. And finally, we got to probably not that visible, but on our benchmarks, it was a much better tool, KT-FMT. Again, it's open source, so feel free to check it out if you're interested. All right, done with tools, and the next main chapter in the Kotlin development is libraries, and how we adopt the libraries not to be some sort of wrappers over the old Java code, but for Kotlin to become a first-class citizen in the code base. So here are a few rules that we applied in the code base. First of all, it's always better not to use CodeGen, but if you have to, KAPT is not a great option, and now it's getting to its sunset. However, we realized that either a compiler plugins, Kotlin compiler plugins, or KSP, which is sort of a new thing, they work better and more performant in our code base. However, if code generation is not necessary in your case, and there were a few libraries where we didn't end up using the CodeGen, it's always better to avoid it. So Kotlin language features are not surprisingly in the Kotlin compiler frontends invoke a lot of code generation. So it's possible to rely on Kotlin itself to provide the CodeGen you need, but a faster one. And finally, better to do and provide the idiomatic Kotlin APIs rather than wrapping the old Java ones. For example, it's possible to provide libraries like FB, KTX, which is a sort of a number of extensions that previously supported the Java libraries we did. There is a good example of no code gen solution. So we have a lethal library which is responsible for our declarative UI, and this is how we moved from the code gen style, which is very popular in Compose these days, to the non-code gen at all, and composable. All right, we created some code. Now it's time to build what we did. And we start with the build system. Can we use a familiar in Android world Gradle? Sadly, no. Meta uses bug. It's not from the very beginning bound to any concrete language like Java or Kotlin, so it's a general purpose language. It has the explicit dependencies, inputs, and it tries to be as no or low side effects as it's possible. So it's most of the time always possible to make builds reproducible, and but also encourage smaller modules, which is really a selling point on the high scale. It allows a better parallelism. So from the main difference between Bug and Gradle, it's a different module structure, a different configuration language, and almost everything is different. So it's even like a bad comparisons. It's also open source, and it's interesting that Meta and Facebook at that time was not the first company that introduced Kotlin support in Bug. So it was originally made by Uber, and then we just polished it, added a few optimizations. Some of them I will touch in the next slides, but it's now slightly a better place to host your Kotlin builds. So what happens when you build Kotlin with Bug? So almost all the familiar problems from the Gradle world appear here. Compiler is slow, relatively slow compared to Java. Annotation processor is like by far slower than Java annotation processor. And on our modules and our benchmark, we saw 2 to 2.5 x difference in the build times when we first interacted with Kotlin. It's improved slightly, however, with the adoption growth, these numbers are getting better. And should we just live with this difference, or it's possible to improve something? So we need some sort of a hero, and in the Kotlin and Java world, the hero is the ABI generation. ABI is the general public interface for your module, which contains only the public parts. So, and these public parts are the thing that you can use when you compile the dependencies. So, application binary interface. Let's briefly get to what it is. So imagine we have a sort of a class. In this case, it's a render unit. What we need to remove everything that is private in this class. So in this case, we just remove private final variables, some method bodies to keep only the thing that is possible to invoke from different modules. And this is finally what we are getting. It's called the ABI. ABI has some benefits, namely two. It's not necessary to rebuild your dependency module only if a private thing in ABI changed. And this private thing is actually not a part of the ABI. And with ABI jar and building against ABI jars, it's possible to save networking and RAM when you compile. So you don't need to process and pass to class pass the whole jars, which are significantly bigger than just the overall ABI representation. All right. Let's check out how do we do compilation when ABIs are in charge. So we are trying to build the app which depends on the light support. And this light support library, let's imagine that we are going to change it. So if we just change it, what we need to rebuild? We need to rebuild the app and the plugin which depend on the light support. So almost the whole project, and then we need to rebuild the dependent adapter on plugin. So just events are something that we didn't touch. All right, and now let's compare it to the case where we build something against ABIs. And against ABIs here means against the class ABI. It's a sort of a type of ABI generation. Now we have slightly more building blocks in this chain. However, let's say we modified something private in a live support. So what does it mean for us? That now we also need to rebuild light support ABI. But we know that light support ABI will not change because we modified the private thing. And then we need to rebuild an app. So instead of rebuilding almost the whole application, we ended up rebuilding only 3 blocks. Quite an improvement. So, and we saved build time because some of the things were in the build cache. Cool. Then, is it possible to do better? To answer the question, let's try to understand how Java compiler compiles a module. Yeah, it's probably a good history lesson. No one uses Java anymore. What Java compiler does, it first enters the parse and enter stage where it do all the manipulation with something as a text. Not all of the types are available at this point. Not all of them are resolved. However, at the end of this stage, it's possible to figure out the ABI. And we are actively utilizing this thing because we can just ignore the analysis and generation stage and get ABI earlier. And it means probably saving on the compilation 2 times or whatever and getting the ABI earlier. Let's now try to understand how we can apply these changes. And the answer is source ABI, and it's the generation mode where we, instead of building ABI and full jars in a sequence, we invoke parallel actions and we build a full jar and ABI jar simultaneously. In this case, if you modify the live support, we simultaneously can start building live support ABI and live support the full jar, and we are sort of flattening the build graph. If we use the parallel execution, it just goes much more faster. All right, but what if we can do something even better? There is a technique called a source-only ABI. And this means, let's stop compiling our dependencies at all. And let's say, if we have an import for an extension here, what is it? What is this extension? So we see it's somewhere imported from the extension render core Facebook.com. Likely it's a class. So what if we just pretend that it's a class? The same, if we have a screaming underscore case, what if we pretend it's a constant or a static import? And surprisingly, it works amazingly well. And in this case, it's possible to start building all ABIs that support this kind of heuristics even earlier. And these flatten the graph even more. Let's just try to compare these two. This is a basic ABI compilation, and this is the source-only ABI compilation. So you can see the critical path is just 2 times shorter. And that means if we have quite a powerful machine or remote execution, we can in parallel compile everything, and developers will not just notice that we are slow with Kotlin. Some of the wins here. With class ABI, we got 35% of reduction in the rebuilds. And on top of this, with the source-only ABI, we got 77% less hopeless cache fetches, and our build time increased by around 30% for Instagram. All right, it was everything about Java compilation, but what is with Kotlin? So the class ABI, we already ported it to Batch, so it's publicly available. We have some optimization that are available on top of this, so it's completely not a problem and usable. For source-only ABI, it's possible. Probably it will be a talk later, maybe Kotlin Conf or whatever. It's something that we are considering to put to open source as well, and if you are interested in this being an open source, you can message me on Twitter. All right, now we built our code. Let's try to understand what we need to finally ship it to our users. I mentioned the slightly bigger APK, but how to make it slightly bigger, but not giantly bigger, because you know, Kotlin has a lot of synthetic sugar. To answer this question, we quickly need to recap how we do things in Android up to getting the actual APK. So we have, unsurprisingly, sources, resources, multiple languages. I'm very sorry for the guys who love Scala and Groovy for not including the compilers on this picture, but then we have a few compilers that compile all the code for us. We have dexers, because we finally need to move from the JVM and bytecode to dexcode. And the interesting part, the most interesting part for us here is the way how to shrink, optimize, and add obfuscation. And these are the 2 building blocks here, R8, regex, and progrart, that we will touch soon. So finally, after all, we are building the APK that is possible to ship. There are multiple dex bytecode optimizers available. So it's quite hard to understand which one to use. But Google made it slightly easier for almost everyone. So stick to R8, open source one, and if you feel like you want to explore the alternatives, probably you understand what you're doing, so you don't need my help and advice here. So Redux is a meta alternative for dexcode optimizer. It's open source and widely available. If you're at the point where deciding between those two, it's better to treat both like a black box and just see what results you're getting. Before getting into concrete Kotlin optimizations, we need like a few blocks of what they are built from. Probably the most simple optimization there is in the world is the method inlining or function inlining. So whenever you just have a function and there is only one or a few places where you can invoke it, whatever say you inline it. Probably the second simplest optimization is the remove unreachable. If you don't need something, if something is a dead code, just don't include it into the dex. So like here. And then, on top of this, we can apply inlining or constant propagation once again, so it works well. And the interesting thing is you can apply multiple rounds of inlining after different optimizations, so it's all composable in a way. But what makes Kotlin so special that we need to apply new techniques here? Mainly a synthetic sugar. And let me try to guide you through just 2 most interesting optimizations that we applied in Redux. They are partly available in R8 as well, so you probably are benefiting from them already. The first one is the lambda expression optimization. So this is just a primitive lambda, and yeah, unfortunately this is the bytecode that it generates. So it's sort of a wrapper of anonymous class, placeholder, and a lot of calls inside. The most important part for us here, there are many invocations inside. And just to prove that in a DEX code it doesn't go anyway, so this is the DEX code the bytecode is translated to. So what happens to lambda expressions at scale? Let's imagine we have 10,000 of these calls to lambda in our code base. And a simple calculation suggests that it will get us to 30,000 of methods, 10,000 of classes, and 10,000 of callbacks, which is for these guys, this metadata, instances, whatever. It's quite a lot, and you don't want to handle all of them. So how to fix the thing? There is the technique which is known as lambda grouping or class merging, which is implemented in both R8 and Redux. The basic idea, let's target the classes with the shape that is somehow similar to a function and then merge them. And inside the thing that we merge, because function could be different, let's try to have some kind of a switch. And this type in the switch is the only thing that will represent the initial class of function that it was. So based on this technique, it's possible to create the stuff for invoke function, for the init constructor, and many other things. The only place in code where you need to really hard fix the thing is the casts, because as previously you had some sort of the functions that are syntactically generated. Now it's an Uber function, and you need to understand where you change the type. Why not to use a simple inline? The answer was on some of the previous slides. So inline function is something that we need to have in ABI together with whole of its body, and it means increase the ABI size probably several times if we put it all together. And this is really bad, and that degrades the build speed. And you just, whenever you place the private changes, they will be in your ABI. So it's not the option based on the build speed, sadly. All right, the last one probably for today. It's the data class. A very great thing, and currently in Java we also have records, but it's a different story. Really good to store your data and express it. Sadly, comes with the overhead. These are all the methods that we have in the person class. Yeah, I talked you through the R8 and Redux. Let's try to understand what it already can optimize in data classes. It can optimize getters with inlining. It can optimize the component and method with either remove unreachable passes or, again, inlining. Same story for copy and synthetic copy with a default. If we don't use them, we just remove the unreachable. If we use them, then we inline them. Pretty simple. The hard ones, toString, hashcode, and equals. The only thing that is common for all of these things is that they override the object or any type methods. And this is just what you get from the simple, typical toString method in a data class. It's like a lot of overheads. So what we had to do, we had to implement a thing called data class generate that explicitly said what methods we want to keep inside the data class with several modes. And after that, we saved a significant number, which is close to several hundreds of kilobytes or kibibytes in our applications, just by placing this on almost every data class in an app. All right, state of adoption, where we are now. IDE functionality and usage, it's mitigated, so we can easily develop on the medium to high scale. The app size regression, the problem is solved, so we are no longer invest a lot in this area. And the build performance, unfortunately, it's emerging with the increase of percentage of Kotlin in our code base. And we have to invest a lot in our toolchain upgrades. We explore K2 compiler. We explore several more optimization that I just highlighted before. And finally, takeaways. Kotlin adoption is for a high scale, sadly a marathon, not a sprint. So we have to invest probably for several more years, maybe for a really, really long time. And we have to maintain the Kotlin Foundation team just for these reasons. Any even small inefficiency in an app at scale is a huge difference. So for example, a toString, you just blow up users with unnecessary toString methods. And the great one, so developer happiness worth all of this suffering for infrastructure team and for me personally. There are some links to the open source thing I mentioned before, and thanks a lot for coming today. That's it. Any questions?